All right, for today's video, I'd like to introduce the idea of osmosis. Make sure we really fundamentally understand what osmosis is, and then apply that in terms of osmolarity and tonicity, and explain, especially from a medical point of view, why that's so important and what we can do with that knowledge. First, I'd like to introduce you to this guy. This is my version of a YouTube. Pretty nice, right? My question is, as you can see, we've got a pitcher of water. We're going to pour water into one end of this tube. And because of its shape, we kind of understand everything that's working against it. We got gravity, we got pressure, air pressure. All these things combine, even though we don't really consciously think about it. But this is my question. As we pour water into one end of this U-tube, and let's say the water level is about right there on this side. Can we predict with any degree of certainty how high the water will be on the other side? And of course, the answer is yes. Hopefully, this is pretty obvious to you because of the things we just mentioned, gravity, air pressure, all of those things. We know that water on that side is going to be the same level, right? We put it on one side, but it's going to fill up equally on both sides. That seems to be pretty straightforward. Well, let's take this same experiment, and now let's change it up just a little bit. I'm going to go across the street. Obviously, I would never do this to my own house. No, don't go across the street. I'm going to take a screen, a mesh screen off of a window from my house. I think everybody knows what we're talking about. And I'm going to put that screen right here, right in the middle. Now, this mesh wire screen acts as a semi-permeable membrane. It's big enough easily to let water through, but it's not going to let bigger things through like rocks. So this is what I'm going to do. I'm going to dump that water in again with the screen in place. As from what we talked about just a second ago, we're going to fill it to that level, and we can predict, because water freely moves right through that screen, that we're going to have the same water level on this side. But now we're going to do something different. I'm going to take some rocks that I dug out of my garden. Okay, this is a rock. And I'm going to dump the rock in. The rock can't go through my semi-permeable membrane. So the rocks are going to stay on this side of that screen. There's my pile of rocks. Can I predict water level changes? What's going to happen to the right side of this U-tube? Because I've added because I've added rocks, and rocks take up mass, right? They take up this volume. I hope we can all appreciate that water levels are going to rise. So we've got a new water level here because of the volume taken up by the rocks. But now we ask the same question. Can we reliably predict what happens on the other side? What happens over here? Does the water level stay the same? Does it go up, or does it go down? Remember, the rocks are only on one side. As you think about this, I hope you can appreciate that, of course, the water is going to also go up to match the new level. Just because we have a screen in the way, that doesn't change the way water is displaced, and water is going to stay the same on both sides. Hopefully that makes sense. All right, let's complicate it. We are going to once again add a semi-permeable membrane. This time, the semi-permeable membrane is actually an official semi-permeable membrane. This is a cell membrane, a lipid bilayer. And as we've learned in previous videos, we know that most things can't get through this membrane. Small, nonpolar, non-charged, lipophilic, those things can move through. But for this membrane, we're going to add some aquaporins to it. That's a channel for facilitated diffusion to let water go through. So in this cell membrane, water is permeable. It's permeable to water. but not ions. Okay, now we have our semi-permeable membrane in place. We are once again going to add rocks. But this time, our rock is a little bit different. This is rock salt, primarily sodium chloride. So we start with our water level. We know it's equal on both sides. And then we add our rock salt. We are taking up volume with the rock salt, just like we did before. And so we can predict water level is going to go up. But what about this side? Well, this is where it gets tricky, because in this scenario, water level goes down. How? Right? Mother Nature's ticked right now. We just upset gravity, air pressure. All these things are trying to keep water level the same, but we have disrupted it, and we've seen water go down on one side as it moves to the other side. This is osmosis. But we have to understand why. What's the driver? As we look at these two different scenarios, what's the difference? Right? We added rocks to one side. It's a semi-permeable membrane. The rocks stay on one side. And yet, in one, water goes up equally on both sides. But in the other, water goes up on one side and down on the other side. The difference is simply due to the fact that salt is soluble. The rocks that we added above, they don't dissolve in water. They just sit there. But the salt dissolves. Because it's held together by an ionic bond, it also dissociates. But anything that dissolves, we could do the same thing with sugar, with glucose, and we would see the same effect because it's soluble. Now, why should that matter? Well, let's make sure we understand what solubility means. It means that water binds to this substance. It forms a hydration shell around it. That's what it means to dissolve. Let's see if we can't draw this out and better understand now why water is going to behave so differently. Let's change all of these rocks to the ions that they are. Let's go back over here to the original amount of water, and we add sodium. Right? And we'll just use pluses for sodium. And we've got chloride as a negative ion. And on both sides, let's have the same amount of water. But let's just draw the water out this time as individual molecules. So let's say on this side, 1, 2, 3, 4, 5, 6, 7. We've got 12 on that side. We'll make sure we have 12 on this side. We have the same amount of water. But because we now understand what it means to be soluble, we can see a difference. Now, I'm not saying that it's a 1-to-1 ratio like I'm about to draw it. It's going to take a lot of individual water molecules to bind up the formal charge that it is on sodium or on chloride. But for this little experiment, let's just look and see what happens if we tie these up in a 1-to-1 ratio. So that means this water is bound to that negative. This water is bound to that positive. That one's bound there. That one's bound there. That one's bound there. I hope you can see what we've just done. If we go back to our video about movement, we saw that movement was based on, and we're talking about passive movement, based on stochastic odds, right? Random movements. But the probability of movement was different if we had a concentration gradient. Well, now let's apply that to water. Even though we have the same amount of water, and that's where it gets a little tricky. We have the same amount of water on both sides. We do not have the same amount of what I would like to call free water, water that can actually move through the membrane. Because remember, this membrane is impermeable to ions. So the sodium, the positive, it can't get through. The chloride, the negative, it can't get through. And so all water molecules tied to those charges, bound to them, is blocked from moving. So we see that we have 12 free water molecules on this side that are able to move. And we can represent that with this arrow. But over on this side, I only count 2 water molecules that aren't bound to ions. So there's only a very small chance that that water will move. All we have to do is look at these arrows now and see that we will have a net movement of water down water's concentration gradient, talking about free water, the water that can actually cross this membrane. Of course, that seems really weird because there really isn't a concentration gradient for water. But so how do we describe this? Well, instead of saying water moves down its concentration gradient, what do we say instead? We say water moves up the solute concentration gradient. In other words, and just remember this, right? Water follows salt. So just to visualize that again, if we come back to our tube, we see all the salt on the one side, we see water bound to that salt. That water cannot move. And so in the spirit of true diffusion, as water seeks an equilibrium, water will move to an area of high solute concentration. Water follows salt. And that is osmosis. So let's define that. Osmosis, the movement of water up a solute concentration gradient. I'd also like to define the idea of osmotic pressure. This is the amount of pressure just enough to resist that movement of water. That's kind of a complicated thing. But think about, for example, blowing up a balloon. The more air I put into the balloon, the tighter the balloon gets. And there comes a point where I can actually rupture that balloon if I put more air in. But I hope you can appreciate, once I get air into the balloon, it's fairly easy to blow up. But as it gets tighter and tighter, the pressure pushing against me is higher and higher. And that's the same idea behind osmotic pressure, right? If we go back to these water values again, we can see that I've got a lot of water up here. I've got less water on this side. But remember, Mother Nature's not happy. I've got gravity pulling on all the things equal. I've got air pressure pushing on all things equal. And so there is going to come a point where moving more water is actually going to be very challenging. Even though water wants to go that way, the pressure that it's pushing against is higher and higher. And so that's the idea behind osmotic pressure. The pressure pushing against the water movement. All right, there's osmosis. Now let's see if we can take this and apply it to a scenario in the body. Now we're talking about osmolarity and tonicity. Let's first define these terms. Osmolarity is simply a concentration. It's just a concentration. And because we know that concentrations are just a ratio of stuff over volume, the units of osmolarity, it has units. So concentration in osmol per liter. That's what osmolarity is. Tonicity is a little bit more abstract. Tonicity doesn't have units. Tonicity is a prediction of water movement into or out of a cell. Okay, let's see if we can figure this out. I'm going to draw some beakers. And inside these beakers, the first one, we're just going to have straight up water. In the second one, we're going to have water plus salt. So the concentration, we're going to have it at 0.9% NaCl. And on the other one, we're going to have sugar. And we're going to call it, we're going to say 5% dextrose, which is just D-glucose. So that's glucose. So water, 0.9% salt, 5% dextrose. All right, first let's compare osmolarity. Remember, osmolarity is just a concentration. It's in osmols per liter. Of course, percent, we need to change some units to convert that, but we can do that mathematically really quick. A couple of things to think about when we look at these values, and this will come into play in just a second. 0.9% sodium chloride is about 300 milliosmolar. Likewise, 5% dextrose is also about 300 milliosmolar. So let's compare water to the salt concentration. The other thing as we do these comparisons, hypo equals less, iso is the same, and hyper equals more. So, what is water compared to salt? Well, water is essentially zero, right? There's nothing in here. Salt, 300 milliosmoles per liter. Dextrose also 300 milliosmoles per liter. This water, if we were to compare the water to the salt, the water would be hypoosmotic. The salt would be hyperosmotic, right? If we're making that comparison. But what if we're making this comparison? Both are at 300, and so this would be considered isoosmotic to the salt. Hopefully you were able to follow me on that. What about tonicity, right? Osmolarity is easy. All we're doing is we're comparing concentrations. And we see if it's a higher concentration, it's hyper compared to what we're looking at. Or if they're the same, it's going to be iso. If it's less than, it's hypoosmotic. Tonicity, though, is just a little bit different. For tonicity, I have to predict what's going to happen to a cell. So let's have a cell sitting right here. For tonicity, another rule. The cell, we're going to assume, is always going to be equal to 300 milliosmolar. So the same as the 0.9% saline or the 5% dextrose. We are 300 in here. Now, if I'm comparing the two, let's just start with the water. The water compared to the cell's at 300, the water's at 0, and the cell's always going to be our reference point. So the water at 0 compared to the cell is less. Therefore, the water is hypoosmotic. But what about tonicity? Well, for what we learned about osmosis, we know that water is going to follow salt. And because the cell is 300 and the water is 0, the question is, when I take that cell and put it inside the cup, right, we're still 0. We'll draw it up in the corner here so we have some room. And here's my cell, and the cell's 300. The question is, what's going to happen? Well, water follows salt. Hopefully we can see that. The water sees 0 on the outside, 300 on the inside. Water will go into the cell. That's going to cause the cell to expand. It's going to swell up. If it's strong enough, it could actually even pop. It could burst. And so this is what a hypotonic solution does. It causes a cell to swell. Well, let's do the same thing over here. Right? If we put water inside the salt, of course, we're 300 in here. The cell is at 300. And so we are isoosmotic, and we are also isotonic. Because there's no salt gradient, there's no net movement of water, and as such, the cell stays the same shape. All right, what about this one? Makes sense that it would do the same thing, right? So we're 300 in here. The cell is also 300, so we know they're isoosmotic. They have the same concentrations, and yet this is a hypotonic solution. water will go into the cell and cause it to rupture. Why? What's the difference between the salt and the sugar? Well, let's draw the cell in a different way. Let's draw it like a Pac-Man. Sugar's delicious. And every chance that the cell gets, what does it do when it's got sugar around? It eats it. So all of this 300 that was in here, it ends up going into the cell to be processed by metabolism and turned into ATP. That doesn't change much about the cell. The cell's always at 300. But outside, after all the sugar is gone, what am I left with? I'm left with 0. So, for tonicity, only count salt. Because salt isn't let into the cell, but sugar is. Now, the caveat is we're talking about normal situations, right? If somebody's diabetic, they have type 2 diabetes, which is characterized by insulin resistance and the inability to move sugar into the blood. Now it matters, right? Because now buildup of sugar in the blood, because it can't get into cells, will certainly affect this. But under normal conditions, as blood sugar goes up, insulin is released, lets that blood sugar into cells, blood sugar is maintained. And so that's why we don't count sugar for tonicity in a biological setting. My last one, let's apply this in kind of a strange scenario. What if we have a solution? Here's my beaker, and this solution is 5% dextrose and 0.45% or half normal saline. Okay? Think about this for just a second. My question is, what is the osmolarity and what is the tonicity of this solution? Well, for osmolarity, remember, it's just concentrations. And because it's osmoles, we're going to add up all the stuff that's in there. So let's start with the dextrose. We know the dextrose is a 5% dextrose. That's going to be 300, right? This is for the dextrose. For the salt, 0.9 was 300. 0.45 is half of that. So for the salt, we've got half of 300, which is 150. The total sum of that gives us 450 milliosmoles per liter. The cell, if you recall, is at 300. Because 450 is higher than 300, what's the osmolarity of this solution? This is a hyperosmolar solution. Its concentration is higher. But for tonicity, what's going to happen to the cell when I stick the cell inside? Well, if we think about what we're doing, we're only counting salt because salt is the only non-penetrating or impermeable solute. That means that this 300 doesn't count. Why? Because the cell's going to eat it. That means that we're no longer at 450, we're just at 150. And because 150 is less than 300, the tonicity is hypotonic. In other words, as I put the cell inside that solution, the cell will swell because water is going to the higher salt concentration. Of course, if we come up with a higher salt solution, right? If we had something like, a 1.2% sodium chloride, the minute the salt concentration gets higher than 0.9%, now by default, it has to be hypertonic. And what's going to happen in a hypertonic scenario? Well, this means that water is going to go from the cell into the solution because that's where the salt is, the higher salt concentration. This will cause the cell to crenate, in other words, shrink. So in a hypertonic solution, the cell shrinks, whereas in a hypotonic solution, the cell swells. Hopefully this gives you a solid understanding of osmosis and then osmolarity and tonicity and how we can predict the movement of water into and out of cells.